Thank you for joining us today for EPA's Tools and Resources webinar series. Today's webinar will highlight cost-effective treatment technologies for small drinking water systems, and specifically a biological water treatment technology that EPA's Office of Research and Development has developed and patented that removes ammonia. If you have a related science question during or after the presentation, we invite you to type it into the chat pod. And once the presentation ends, we will answer as many questions through the chat part as time allows. You can listen through your computer speakers, or you can also dial into the phone line, and that number is typed in the chat pod. We are going to post the PowerPoint slides from today on EPA's website by the end of the week, and Amy has typed that web address also into the chat pod. So I'm going to go ahead and turn it over to Joe Williams. Joe is the Deputy Director for EPA's Safe and Sustainable Water Resources Research Program, and he is going to introduce the topic and our speaker for today. Joe?
Thank you, Lisa. This is Joe Williams, as Lisa mentioned. I do welcome everyone to the webinar today, and wanted to just say this is one of our shining stars, if you will, for our pilot to full-scale application that our speaker will be visiting with you about and describing to you. Our speaker today is Dr. Darren Lytle. He's with ORD's National Risk Management Research Laboratory in Cincinnati. He comes to us from backgrounds in civil engineering and environmental engineering, with a special focus in corrosion control, water quality. Been working in those areas since 1991 and coming to EPA. So with that, I'm going to turn it over to Darren and let him get started. But thank you for coming and being a part of the webinar today. And Darren, I'll turn it over to you.
Just one quick thing. Go ahead, Amy.
At this point, I'll be muting all of the lines.
Okay, so
the leader has muted your line. To unmute your line, press #6.
Okay, Amy, can you hear me?
We can hear you. Thanks.
Oh, perfect. Okay, so yeah, thanks a lot for the introduction, and I appreciate the opportunity to speak to you today. I want to start things off with kind of an introduction as to how we bring our work and technologies and approaches to the regions, states, communities, and how we work and partner with industry as well to protect public health. So I've kind of got this this schematic, this flow chart, we'll say, and it's, we start out, and we're a research group, so we start out with ideas that we develop and come up with oftentimes through observations. And in the case of what we're talking about today, we observe some things in a full-scale plant with respect to ammonia removal here in Ohio. But we took that idea and we developed it in the laboratory and evaluated it through bench scale studies in our laboratories here in Cincinnati, where I'm located. And so, once we developed the technology at the bench scale and even at the pilot scale in the laboratories here, we have to get that research and that idea out into a pilot scale situation in the field, because we're limited, of course, with what we can do water quality wise and things here in the laboratory, and we always want to go into the real world to pilot and evaluate these technologies. So the next step in that path is after we come up with the idea and do our work in-house, we move on to some sort of community engagement where we look for communities or we work with states or regions to find communities that might be interested in evaluating and have a need to evaluate the technology approach that we're looking at. And if appropriate, this is a time too where we go to our technology transfer folks and we look to patent. And there is an interest in the agency from the agency to patent some of our ideas. And so when there's an opportunity, we also take that pathway as well. But when it comes of the community engagement, you know, we pilot the idea at the community, we demonstrate it, and that's what I'll be talking about. And if that technology works, you know, it needs to be accepted, and it needs to be taken on and accepted by the state, because at the end of the day, when we talk about drinking water anyways, the states have to approve and accept those technologies. So based upon the pilots that we do in communities that have a need, you know, there's a report that's produced, and from there, it needs to be accepted by the state. And once it's accepted by the state, it moves on then to the full-scale design. And along the way, our stakeholders, states, the small systems, consulting firms that work for the small systems are engaging in providing input along the way. At the same time, too, if there's a patent that's filed, there's always an opportunity for us to work with industry and license that patent to them. And so we'll talk a little bit about that as well. And then, of course, at the end of the day, you know, our goal is to get that technology out into a full-scale situation and remove the contaminants or contaminant that we're concerned about, and, of course, ultimately protecting public health. So that's kind of the approach, and I'm going to sort of walk you through some of the work that we've been doing, demonstrating kind of each one of these steps along the way. So a little bit of background, you know, we are talking about ammonia, but we also need to talk about nitrite and nitrate along the way, too. And from a regulatory perspective, there is no regulatory standard for ammonia, but it's important, and I'll share with you why in a minute. There are regulatory standards, MCLs, which are enforceable standards that the agency establishes for nitrite of 1 milligram per liter as nitrogen, and then nitrate as 10 milligrams per liter of nitrogen. And, of course, these drinking water standards consider, these ones in particular, the nitrite and nitrate standard, consider levels of the contaminant entering the distribution system and not what's happening in the distribution system. So once the water leaves and enters the distribution system, we don't monitor nitrite and nitrate. We're not required to anyways, to monitor them under the regulations. So ammonia is found in many waters across the United States, particularly where agricultural impacts are felt. And ammonia, while in itself is not regulated, it presents some issues with other water treatment processes, such as arsenic removal. And then, more importantly, within the distribution system, it can be converted to nitrite and nitrate, the two regulated contaminants, which we don't monitor in the distribution system. So I'll talk about, again, why that's important in a moment. So nitrification is, in fact, that process where bacteria convert ammonia to nitrite and then to nitrate. It's sort of a two-step process, and so that's an issue for us. Ammonia in itself, in this process, if it happens within some filters, it can actually foul filters and cause problems with the filter operation. It can create, ammonia in itself can create wastewater discharge issues if it moves through the distribution system and out into the sewage system. It creates an oxidant or chlorine demand, which, of course, we may or may not want. We probably don't want, because that's going to reduce our effectiveness to disinfect. And as a result, it might create some difficulties complying with our disinfection byproduct rules and regulations. It interferes with arsenic oxidation, so that's where we might have some issues with arsenic removal if we have ammonia in the water. And I put a question mark because I'm not totally certain, but I believe there to be some suggestions that it might even interfere with iron and manganese removal as well. But the really big concern from a health perspective is the nitrification in the distribution system. That is, if ammonia goes into the distribution system and is allowed to go out as free ammonia, and it's converted to nitrite and nitrate through the nitrification process, because, of course, we have biofilm in our distribution systems, then we can get all kinds of other issues that we don't want. We can get taste and odor complaints. The process itself, the biological process itself, results in a pH drop, and it's been linked to corrosion as a result of that. It can result in increases in iron concentration, and iron release and iron corrosion. And then perhaps most importantly is you can get high levels of nitrite in particular in nitrate. But nitrite, if you recall, the standard is 1 milligram per liter. And so it's not very high, and certainly that could be an issue, and we've actually seen that. And there's, there's concerns for that from a health perspective, so we need to be really aware of that. So those are the reasons why we want to deal with ammonia in the first place. So we want to get it out. Where's ammonia located? Well, it's located, in a lot of places. This is just some mapping that we pulled data from the USGS's database that they have available online from groundwaters, and I've just marked off, the different colors. The darker you get, the higher the concentration of ammonia. And I pulled out Region 7 because we've done a lot of work in Region 7, but in particular in the state of Iowa, where they have a lot of issues with ammonia in the source water. And so I just wanted to give you a sense for where ammonia is, in groundwaters across the United States. So what are the options? Well, the options are, if you have an high ammonia concentrations, is a couple. There's a few. One is this monochloramine formation, and simply all that means is that we add chlorine to the water, and we try to tie up. So chlorine reacts with the ammonia to form monochloramine, and so we can tie up the ammonia by adding chlorine, and that's fine, but it's a very, very difficult thing to manage because oftentimes the source water has a varying concentration of ammonia in it. Oftentimes small systems or systems are using multiple wells, so that concentration could be changing a lot. And also there's a big cost associated with that because it can be tens of milligrams per liter of chlorine to add to address higher concentrations of ammonia that might be in some water. So there's a cost associated with it that's big as well. There's breakpoint chlorination, and that's where you add a lot of chlorine and you basically break up or burn away, we'll say, the ammonia. And you can do that, but that's even going to be more chlorine, and there's a bigger cost associated with that. And then also, too, we're adding so much chlorine that we're concerned about issues associated with disinfection byproducts because we have a disinfection byproducts rule. There are other options. There's ion exchange, reverse osmosis, and chemical oxidation by other means. But these processes, in particular for a small system where a lot of these ammonia issues focus or hit the small systems much harder in rural parts of the country than other parts, these processes are sometimes complicated, more complicated, more costly, both capital and operating costs. They have residuals associated with them. That is, they have waste streams associated with them that are difficult to deal with. In particular, ion exchange and reverse osmosis have a liquid waste stream. And those state folks on the line, you understand that that's a bit of a challenge to get rid of because putting liquid waste in sewers and other places is sometimes a challenge and a limitation. So for that reason, the cost associated with and the difficulties and challenges associated with some of the more complicated systems, biological treatment is what we've been focusing on. So what is biological treatment, and what are we talking about here? So all we're talking about really is rather than having that nitrification process, that two-step process here that I've sort of laid out with equations, the conversion first of ammonia to nitrite by one set of bacteria, and then another set of bacteria take the nitrite and convert it to nitrate, to have that happen at the treatment plant. And if it goes all the way to nitrate, if you recall, the standard for nitrate is 10 milligrams per liter. So it's kind of a one-to-one thing. So in other words, if you have 5 milligrams per liter of ammonia in your water as nitrogen, and you convert it all to nitrate, then you end up with 5 milligrams per liter of nitrate, well below the standard. And so that's what we want to do. We don't want it to happen in the distribution system. We want it to happen at the treatment plant, and we want to encourage it. The key, though, here is the oxygen requirement. It requires 4.57 milligrams of oxygen per every milligram of ammonia to convert it all the way to nitrate. And that's a limitation if we have high amounts of ammonia in the water for the kind of, we'll say, the standard way in which we introduce oxygen or aeration. There's a limitation to how much we can add because it's limited by the saturation state of oxygen in water, which is typically, depending on the temperature, 8, 9, 10 milligrams per liter, which means that, we can only address at the max, milligram and a half or so of ammonia in a water, kind of the standard way we do it, through aeration, step followed by filtration. So that's where our process comes in, is we kind of get over that hurdle through the approach that we've taken. So this is what we want to encourage happen at the plant, not in the distribution system. And so this sort of lays out kind of, as I said, the aeration, filtration, the kind of the standard common ion removal process that probably some of you are aware of, where we introduce air through oxygen through aeration, some sort of aeration chamber or device, and then we follow it by filtration. But again, there's going to be a limit to how much ammonia we could oxidize in the nitrification process, because those aerobic bacteria require that oxygen. So, there's going to be a limit. If we get higher ammonia concentrations, which we do, then we got to go to another approach. There's also this idea of a nitrification contactor, and I'll take it one step further and call it an aeration contactor. And so what the idea, and this is really really the bottom line of the approach that we're taking, is that we introduce oxygen through aeration to a contactor, a column that has gravel in it. And by doing that, the air and the oxygen is always saturated. So as the oxygen is being consumed by bacteria to convert the ammonia to nitrite to nitrate, the oxygen is always being replenished because there's a constant stream of bubbles, there's a constant stream of oxygen being introduced. So that's the idea. And so, as I said, we came up with this idea. Now it's been many years ago, and so we took the idea and we started out just with some mini columns, really mini columns. And you can see there's a couple fingers here. So there's some small columns, and we demonstrated that we can oxidize the ammonia effectively. And we actually took some filter media from a full-scale system in Ohio, where we started thinking about the process, and brought it down here. So we had the natural bacteria that were already there to do the oxidation, and we went ahead and demonstrated it. Once we demonstrated it, we moved to kind of a bigger, like a 2-inch diameter kind of pilot study in columns, and started introducing this idea of introducing the bubbles from the bottom and allowing the bubbles to go up through the media. And we were able to really, tackle high concentrations of ammonia that you couldn't do if you just introduced the air before the filter with the gravel in it. So this idea of doing the bench scale studies really allowed us to prove the concept and the idea. It allowed us to establish, engineering and operating parameters, identify limitations, and of course then we from there we built kind of a standard pilot system that we are now ready to approach someone and demonstrate it in the field. So this is where somewhere down the line we got connected with the state of Iowa, and I don't remember exactly when and where, and but I think I gave a talk on what we were doing, and someone approached us from the state and said, hey, we have some issues with ammonia, and I was interested in that they address and look at nitrite and nitrite and nitrate in the distribution system. Unlike it's not required, but unlike other states too. I mean, no one's really looking at it. But because they have such many waters that have high concentrations of ammonia, they're very aware and up on this issue of nitrification in the distribution systems, and they want to address the ammonia. So we were connected with them, and approached with them about our technology and working with communities in their state. And so together we came up with some communities to work with, and we reached out to the communities and were able to find a connection with the communities with the Iowa DNR's help. And they've been absolutely wonderful to work with. And this allowed us then to find a community. And you just can't choose any community. I mean, this is where we just can't do this on our own, because at the end of the day, the community has to be engaged too. They have to have a need and a want to do the work, because we can't be there to sample these things, to monitor these things. They've got to be taking the samples and sending them back and forth. So we got to get community involvement in as well. So the Iowa DNR knows their communities. They connected us up with the right communities who have the interest, who have the need, and have these high levels of ammonia that they want to get rid of. And again, because Iowa is sensitive to the high ammonia levels, they know they want to get rid of them. So it was a perfect fit for us, and a connection. And of course, the state is very engaged as well, because they, and we want them to be engaged, because we want them to communicate, concerns and anything along the way to help the process along and make it a success. So they connected us with the city of Palo, Iowa, and this is a community, a small community of under 900 people. At the time, they didn't have any citywide public drinking water systems. They were on individual wells, but they had some contamination issues with the local river. It's been an issue on and off for years, I guess. flooding, and it contaminates the wells, and so it's a big issue. And so they wanted to go to their own full-scale system. They wanted to put in a community-wide treatment system and distribution system. They received money through a community development block grant. And so that's what they did. They built a whole new distribution system and a whole new treatment plant. And at the time, the only contaminants they had to deal with were ammonia and some iron in the water. And so perfect for us. This is an opportunity to start fresh. So we went in there and we did a pilot system. And then again, this is the technology. Again, and it turns out it's a patented technology. So along the way of doing the work in the lab and in the pilot plants here in Cincinnati, we applied for a patent. So again, this is kind of the process. Again, the idea is the bubbles go up through gravel. They can travel through the gravel, maintain dissolved oxygen concentrations throughout as it's being used up by the bacteria to convert ammonia. It's being replenished all the time. Because it's gravel, it doesn't trap particles. The bacteria attached to it, but it doesn't clog up. And then you have to follow it up, of course, with a true filter, a typical anthracite over sand or some other type of filter that's typically in place for iron removal and other drinking water removal processes that are common. So next step, we got the community, we got the pilot system built at the EPA, we got to move it out, and so that's what we do. We take the plant, we take the system out. Here's our little U-Haul we rented. We took it out to a small system. This is not Palo. This is another community, Keystone, Iowa. But you get the idea. We take it out to the plant. We build it there, and we rebuild it at the site, and we train the staff. And they run it from there on out. It's theirs. They take it over, and they run it, at the plant. Connect it up to their water. This is Palo. There's just a picture of the columns, and again, the aeration contactor idea followed by the standard filter. And in this case, we have three of them, so we can evaluate different parameters. Sort of made the comments about the saturated oxygen levels are kept throughout. Meets all the needs of the oxygen as it's being consumed during the process of nitrification in the columns. It doesn't require much in the way of backwashing at all. These things don't clog up. And again, we follow it up with a granular filter. So this water has over 3 milligrams per liter. So I don't want to get into a whole lot of data in this particular talk, other than point out the fact that we collect a heck of a lot of data. So we collect as much as we possibly can, and the operators on site will do measurements of pH and other things that are required to be managed on site that can't be shipped. But we also, of course, we have one on a weekly basis, samples shipped, and so all this is just looking at ammonia levels and nitrite levels along the way. And again, I don't want to get into the details other than say this water had over 3 milligrams per liter in the source, which is the yellow. And during the pilot, we were able to get these concentrations to very low concentrations. So again, a large amount of data is collected. Palo was the first place that we actually did field pilots. And it's important that we do this because we learned a lot of things that we would have never figured out unless we were in the field. For example, we realized that we had to add a little bit of orthophosphate, a nutrient, to keep the bacteria happy. Would have never figured that out if we weren't in the field actually doing the work. Once we figured that out, our microbiologist got with us and said, I think we have a phosphate limitation here. And so we started adding phosphate, and then, things worked very well. But would have never learned that had we not been doing the pilot in the field. So from the findings, we need orthophosphate addition. Maintaining the oxygen saturation was critical, so you can't let the aerator, these aerators, diffusers, you can't let those things clog up, which they can. So you got to make sure they're clean. We have a little bit of a nitrite spike at first, but that goes away. We developed design parameters, and then, we took this, and again, along the way, we were working with the Iowa DNR, sharing the information, asking if there's anything we needed to do that they would want, because again, at the end of the day, they've got to approve it. That report was actually turned over, and here's a reference to it, so you could actually get it. It's an EPA document. At the end of the presentation, you'll have my contact information. I'd be glad to get it to you. It was also published in the Journal of AWWA as well. But anyways, that report turned out to be the report that the Iowa DNR reviewed and eventually approved. And so anyways, the impact here is that, this pilot study was able to demonstrate the ability to effectively remove ammonia and iron, which also was effectively removed in this community's water. Following the pilot success, more importantly, is that their engineering consultant, who was also involved along the way, was able to take the operating parameters and what we learned from the pilot and take that to a full-scale design. and get that approved, eventually by the state, and then eventually, go full scale with it. Again, it was cost effective and easily implementable. So it was really easy to operate the system. Really easy. Nothing special, no special concerns, residual concerns, nothing that's out of the normal when operating the system. And since we piloted this in other locations as well, in Illinois, Indiana, Ohio, for example, we've demonstrated it as well. Because we figured there's other waters, other challenges. We want to make sure that we try to address everything we could possibly think of. And then again, we've since licensed the technology, which I'll bring up in a second here. So next slide, which is really cool. Really, I have these plans in my office. I mean, it's amazing to see. It's amazing to see, an idea that you come up with in the lab turn into a full-scale plans, which is pretty cool. I'm an engineer, but we don't do this kind of thing. We can take it to the pilot, but that's about as far as we can go. And so H.R. Green and Matthew Wildman designed this particular system, and again, it's pretty cool. I like to show that because it's really nice. The schedule, I just want to briefly mention. This didn't happen overnight. I mean, this is a process, right? We've got an engineering report on the needs of the system. We do the pilot, which is, it took a little longer than normal because we learned some things along the way. And then there's all these other steps that go along the way. Again, they're building their distribution system along the way. There was bids and approvals of the pilots and everything. But anyways, from the time we got started in 2011 to the time that this plant was being, constructed and completed, that's a several-year process. And so I just wanted to kind of highlight that. And the full-scale design considerations and conditions are just sort of listed here for your information. So again, they take the pilot information and the engineer designs it and goes full scale with it. And again, this shows the next slide here is just showing how pilot results feed into the full scale design. And so that's all this is indicating, is that they match up as they're supposed to. That's why you do pilots in the first place. At the end of the day, though, here's what really gets me excited is that we actually have a full-scale system, nice shiny full-scale system. A lot of stainless steel here. These are the aeration contactors, two of them, and two of them. And so this is the idea. This is the patented EPA technology right here. In this picture, there's another picture of them right there, and then these are the blowers themselves. So pretty cool stuff. Beautiful plant. This is the top. So you can see the bubbles coming up, and below those bubbles are the gravel, or is the gravel. Again, pretty exciting stuff. And then these are the filters that follow, pressure filters, and this is pretty standard for iron removal, manganese removal, and other groundwater treatment processes and removal are done through. This is, again, kind of a standard design. Full-scale results. And I'm not sure what's happening here because I don't know about you, but I'm not seeing the graphs. But for whatever reason, they're not coming through. But all I want to say about that is that we didn't just do the pilot. We followed up with monitoring the full-scale system, and sure enough, we see successful removal of ammonia after what we'll call an acclimation period. It takes time for the bacteria to grow. Once they grow and establish, then they're set. And they're hard to kill. In fact, I've never had them killed in the treatment process. They've been, they've operated, and I think Palo's been in place for several years now, and everything's running great there. So, sorry about I'm not sure what happened to the images, but as I said, we are sometimes encouraged to develop technologies. The agency does patent things, and so as I said, this technology is patented and through. And so we were able to then license the patents and the technologies to anybody who's interested. A company called AdEdge has come to us and has a license agreement with us through our federal technology transfer folks and team, and then we created what's called a cooperative research and development agreement, which is a CRADA in short. And so we've got this in place with a company called AdEdge, and it's just, I pulled this off their website, and what they're marketing, they're calling it pneumonia. So, but it's a system that they have, again, it's the technology that they have a license agreement with us. And so I just wanted to introduce that, and the idea that we do, in fact, work with industry and bringing technologies to market. And so the next slide. So we continue to do ammonia work. Although I would say that we're kind of wrapping it up because I think we've covered our basis. We continue to pilot it, and we have continued to pilot it in 4 locations in Iowa, each with kind of a unique challenge that we wanted to challenge the idea with. Again, I mentioned we have a license agreement with our partner at the moment. One of our partners anyway with AdEdge is a small business out of Atlanta. And our most recent success was a pilot in Gilbert, Iowa. And the cool thing about that was that they had manganese and arsenic and iron in the water as well. And so manganese and iron have what are called secondary MCLs, which are aesthetic-based MCLs, precipitation problems, colored water, things like that. And so it had levels in the source water. Of course, it had ammonia at 3 milligrams per liter as well, but it also had these other contaminants. And the arsenic was the interesting one because it's above the MCL for arsenic as well. So of course, arsenic is not a secondary, it's a primary MCL, so we need to be concerned about arsenic. And so we were able to demonstrate this technology not only addressed the ammonia, but it addressed these other contaminants as well. We had a great pilot. Again, we worked closely with Iowa DNR along the way. The pilot was turned over to them. They reviewed it. And my understanding is the full-scale plans had been submitted by AdEdge and the community and their community's engineer to move forward with the full-scale design. And my understanding is that, in late spring, there might be a groundbreaking for the treatment system plant construction. So that's the latest in situation with the ammonia treatment system. Again, along the way, though, we continue to provide technical assistance where it's needed. We're thinking about using this technology in approaching wastewater type applications as well. And then, of course, we're always documenting what we do and getting it out through outreach, through communications, through talks, through journal articles and what have you. Where we are now is we're kind of taking this model that I introduced in the very first slide, and in our expertise and interest in biological, we really are high on biological treatment. Using natural bacteria to encourage them to do the things we want them to do, and so we're moving on now to nitrate. And again, kind of, at the current time, we're kind of working with some ideas that we have in the lab. Nitrate's a little more challenging because now we want to sort of do the reverse. We want to make the system anaerobic. We want to take the oxygen out of the system and convert nitrate to nitrogen gas and just blow it off out of the filters or contactors. So, but it's a little more challenging. Anaerobic is more challenging, and it requires different, we'll say, nutrients and things to introduce to the water. So that's where we're at, and we're interested in we're almost to a point where we want to be getting into engaging our regions and states and communities about looking for possible places to introduce and pilot this in the field. So that's kind of where we're at. We're at a point where we're pretty confident with the technologies and ideas that we've had in the lab, but we're almost ready to go into the field. And so certainly, if you're a state person and you have some interest in nitrate and you're struggling with it, feel free to reach out, to me, and we can talk more about what we're thinking about. Nitrate's a big challenge, and right now the best thing going is anion exchange. So it's ion exchange to remove anions, and that again, requires brines and regeneration and liquid waste that have a lot of nitrate in them. And it just seems like, if we can take nitrate to nitrogen gas, our atmosphere is nitrogen gas, largely dominantly, and it seems like it's the way to go. And using natural bacteria is pretty cool idea. So, anyways, we're working on in-house on that process. Again, we're looking to potentially identify communities. Of course, our partner folks in Iowa have nitrate issues too. So certainly we've talked to them. But again, if anybody wants to talk about it, feel free to reach out to me later. So to wrap it up, I got a nice picture down at the bottom right-hand corner. That's not me in those pictures, but that's one of our technicians and one of our former students one of our students, and our technician, Dan Williams, who builds all these pilots, by the way. We build all these, and he's really handy. He puts together these systems, and then this is one of the operators from, I believe that's Keystone, Iowa. But we all love going out and working closely with communities and states. I mean, it's what gets us out of the office and gets us in touch with the real world. You know, at the end of the day, we can evaluate our technologies and do everything we do in-house. But if it doesn't make a difference, if it's not protecting public health, then we got to reassess that. You know, but I know that what we're doing, you know, here is getting out to communities and making a difference, and that really is, you know, that really makes us happy around here. I mean, that's what we enjoy doing. So to wrap it up, you know, I hopefully I've convinced you and talked to you about you know, this technology that we've developed. You know, and it's not only able to evaluate or remove ammonia, but also too, we're having some success now with arsenic and iron and manganese, which all have MCLs or secondary MCLs. And I discussed why ammonia is important too. You know, it's an aerobic biological treatment process, and it's relatively simple, and again, shown to remove multiple contaminants. There are many factors, you know, through our evaluations, both in-house and in the field, you know, parameters that are important. I mean, I wasn't going to get into details about, you know, evaluating the gravel size. I mean, that makes a difference. How fast the water goes through the filter and the contactor, that makes a difference. Talked a little bit about the phosphate addition, oxygen level. So there's a lot that goes into this. They're kind of behind the scenes that I really didn't share, but I'd be glad to if anybody's interested. It's robust. You know, sometimes people think biological treatment is not robust, but let me tell you, there have been plenty of times where these columns have run dry, and they don't completely dry out, but they run, you know, without water in them because the valve broke or something. You know, that's happened. And as soon as we introduce water, they're back doing what they were doing. I mean, it's pretty unbelievable. It's a viable option for the small systems. You know, we're focused and really interested in small systems because, as I think everybody is aware, I mean, small systems have certain, you know, needs. They have certain they oftentimes have staffing limitations, and we got to keep things somewhat. We can't get into complicated treatment options, and they have a lot of things going on. And so this process is, in fact, simple. I don't have cost analysis, detailed cost analysis for you, but I can assure you that that we don't have the big chemical cost, and we don't have the big residual disposal cost and the other costs associated with some of the more complicated options here. Even the simple options, I mean, the chlorine concentrations that you would need to add to address 3 milligrams per liter of ammonia is a lot in itself. So anyways, and I got to just throw out, you know, I mean, of course, the success is really dependent on our partnerships. It's on working with our states. We absolutely love working with the states, and Iowa's been absolutely great to us in the communities as well. And you know, and I've just, you know, had a great time. I mean, every community we've worked with has been so engaged. It's been unbelievable. And you know, for small systems in particular, I mean, I'm amazed by how knowledgeable some of these people are that we've been working with, and how interested and excited and how proud they've been. You know, at the end of the project, I mean, my gosh, they're so proud and excited to talk about what they're doing, and they share that with others. They share that with other communities within the state. I mean, I can't tell you how many times I've gotten calls from communities, and I said, well, why don't you go check out or give Palo a call, you know? And they do, and it's amazing by how excited they are to share their experiences and their information. And again, hopefully it then, you know, it spreads out, and other people get the benefits of these partnerships and these projects. So I think with that, that's all I've got. Of course, I've got my contact information here, and then I've got some information on our the Safe and Sustainable Water Research Program, which this work falls underneath, and Joe introduced. So that's there, and of course I've got a disclaimer. And with that, I'll turn it back over.
Thank you, Darren.